Welcome to Visual Algebra Lecture 1.2, Groups from Puzzles. In this lecture, we'll see a collection of puzzles dating back to the 1800s that strongly involve group theory. These include the Rubik's Cube, the 15 puzzle, TopSpin, Hungarian Rings, Spinpossible, and more. Let's get started. I want to start with the last slide in the previous lecture because we're going to build off of it. For that one, we had two light switches in the down position. We called this our home state. And we considered the group generated by the actions of flipping or toggling the left and the right switches. So L is what we get by flipping the left switch and R by flipping the right switch. The Cayley graph has the same structure as the group of symmetries of a rectangle. And this was our first example of two seemingly different groups having the same structure and therefore being isomorphic. The formal definition of two groups being isomorphic is technical, and it involves a structure-preserving bijection or one-to-one correspondence between them, called an isomorphism. If two groups have generating sets that define Cayley graphs of the same structure, then they are isomorphic, and we have a yes certificate. So in the previous example, I was able to show you generating sets of the rectangle symmetry group and the two light switch group, which resulted in Cayley graphs that had the same structure. So yes, they are isomorphic. If the Cayley graphs are different, then the groups are not necessarily non-isomorphic, as we saw with the triangle symmetry group. If we used a reflection and a rotation as a generating set, we got this Cayley graph. I've rearranged it a little bit differently, but it's three cycles that go in opposite directions connected by these blue edges. If we use a different generating set, namely two reflections, it doesn't matter which ones. I think in the previous lecture I used f and r squared f, but f and rf give you the same thing. A Cayley graph that looks like a hexagon. So if I just showed you this graph and this graph, at first you don't expect them to be the same group. In other words, a no certificate is harder to verify. If I give you two Cayley graphs that look very different on the same number of nodes, how can you be absolutely sure that they don't represent the same group? And one way to see why these represent the same group is to add these edges into here. And now, if you have this and you remove the red edges and you untangle this little guy, that's a hexagon, you get that. In general, if you want to prove that two groups are non-isomorphic, then we can do this by finding a property that one has, but the other doesn't. And this is a property of the group, not the Cayley graph. It's tempting to go up here and say, well, this one has a 3 cycle and this one doesn't. Well, over here, let's pick one of these states and call it the home state, and you do blue-green, that is a path that takes 3 steps to get back to where you started. So it has to be a property of the group, not the graph. The 2 light switch group generalizes to the 3 light switch group in the, obvious manner. And this group is generated by L, M, and R, which is the action of toggling or flipping the left, middle, and right switch respectively. Like I did before, I'm going to denote these up and down arrows with binary strings and mention that you can think of this group as just the result of adding the corresponding binary strings modulo 2. In other words, here's the home state. Following the blue arrow means adding 1, 0, 0. Following the red arrow means adding 0, 1, 0. And following the green arrow means adding 0, 0, 1. Those are just 3 actions. Of course, there are 8 actions in the group. You can do nothing, or you can do the action of, say, flipping both the left and right switch. So that's this one here. Over here, that means add 1, 1, 0 to whatever state you're you're at. So the actions, the elements of the group are represented by paths, not just edges. Let's now discuss some properties of this group. First of all, this group is abelian. Recall that means that the order does not matter. If you apply A and then B, it's the same as applying B and then A for all 8 of the actions in here. For this, I claim that you only need to check the generators. And notice that blue-red equals red-blue, blue-green equals green-blue, and there's one more, green-red equals red-green. Because if the order doesn't matter for the generators, and you can write everything in the group using generators, then the order doesn't matter for anything, because you can always swap the order of any 2 generators. Another property, every action is its own inverse. So that means that A inverse equals A for all actions in here, or equivalently, remember that means that A squared is the identity. And that makes sense, because if you start from here and you toggle any collection of switches, so maybe you toggle the second and the third switch, and you do that again, you get back to where you started. Over here, that just means that if you add 2 bit strings, modulo 2, so 0, 1, 1, so modulo 2, I just mean even and odd, so 0, 1, 1, so 1 plus 1 mod 2 is 0, 1 plus 0, and 0. So I think this is just saying an odd plus an odd is even, and odd plus an odd is even, even plus an even is even. And finally, any minimal generating set of this group has size 3. And this is not immediately obvious. So it should be clear that this is a minimal generating set right here, L, M, and R. So it generates because it connects up all possible states. And it's minimal because I can't remove any one of these colors. If I remove the red arrows, then I have 2 components. If I remove the blue arrows, I forget what color I used. If I remove the blue arrows, or the green arrows, I get multiple components. It's not clear that there's not some other it's not clear that right away that if you take say the group generated by LM and RL, that maybe you can get all 8 actions like this. But if you check all the cases, there's not too many to check. You'll see that this is not the case. You need 3 actions to generate this group. So this is a property that this group of size 8 has. And as we'll see soon, there's other groups of size 8, and none of the other ones are going to have this property. So if we find a group of size 8 that can be generated by 2 actions or 2 elements, then it can't be this one. They have to be non-isomorphic, and that's the no certificate that we seek. Here is another group of size 8, and this will get us into the notion of puzzles and games. Consider the following rectangle configuration, consisting of do you want to say a black 1 and a white 2, or a white 1 and a black 2? I think I'm going to call this a black 1 and a white 2, even though the actual color of the text is switched from that. We'll call this our home state. And suppose we are allowed the following operations or actions. S is going to be what we get by swapping the position of these 2 squares. So this turns into white 2 and black 1. And T is going to be the action of toggling the color of the first square. So it goes from black to white. Here is a calligraph of this group. And I'm going to call this coin 2. And I couldn't think of a good name for this. And the reason why I'm using coin is because you can actually do this group as an activity in front of you. If you start with 2 different coins. So suppose you have I'm in the US, so I'll use a penny and a nickel, and I'll just denote those with different sizes. So this is heads, and this other one is heads. And then the swap operation is what you get by actually swapping the position of these two coins. And then the toggle operation is what you get by flipping one of these coins upside down. So this is a fun little activity in a classroom to give students a couple of coins and say, how many different configurations can you get from this, and build a Cayley graph. Well, I've built the Cayley graph for you right here. We call this our home state. This is something that, we've seen things like this before. We saw a Cayley graph like this, but it was a hexagon instead of a octagon. So the question I want to ask you is this group isomorphic to the 3 light switch group that we saw earlier? You're probably thinking that the answer is no, because that's why I'm showing you this group. And you'd be right. But let's find a property that this group has that the other one does not. So remember, this is a property of the group, not of the Cayley graph. Well, one property, as we said, is that this group can be generated by 2 elements and not 3. It can be generated by 3, but you only need 2 of them. So right away, we can say that this cannot be isomorphic to the other one. Here's another example. Here's another property. Let's consider the action ST. So if you do that, how many times do you have to do that to get back to where you started? So if you do S and T, so you swap and toggle, you get to this state. You swap and toggle again. You swap and toggle again, and you swap and toggle one more time. This is an element that is not its own inverse. So I'm gonna just write this as ST, and remember we are writing from left to right in this class. And so this element raised to the 4th is the identity. I'll write that as 1. I'm going to write that as E because I have 1 in these used differently here. And also the inverse of this is going to be, well, it's ST cubed. But what is ST cubed? So this is blue, green, blue, green, blue, green. That's just TS. So that's equal to TS. I don't know if you'd consider this little thing with coins or squares to be a game or puzzle, but it will lead us into the topic of this, which is groups from puzzles, and perhaps you will recognize the following. One of the most famous groups is the set of actions on the Rubik's Cube. And of course, most people don't realize this is a group because most people don't even know what group theory is. It's not too involved to show that there are 4.3 times 10 to the 19th distinct configurations of the Rubik's Cube. This is a toy that was invented in 1974 by an architect named Erno Rubik in Budapest, Hungary. His Wikipedia used to say, it no longer does, I brought this up with the Wayback Machine, that Rubik is known to be an introvert and hardly accessible person, hard to contact or get for autographs. He typically does not attend speed cubing events. However, he attended the 2007 World Championship in Budapest. Let me emphasize, not impossible to get an autograph from, just almost impossible. And yes, that is me and Erno Rubik in Budapest in 2010. Just like for the symmetries of the rectangle, the configurations of the Rubik's Cube are different than the actions. But once again, they are in bijective correspondence. The Rubik's Cube group is generated, albeit not minimally, by 6 actions. So we can write them as F, B, R, L, U, and D, which correspond to twisting the following faces: front, back, right, left, upper, and down. Can't use bottom because B is for back. 90 degrees in the clockwise direction. This notation was invented by David Singmaster in the late 1970s, and it's with us today. When I say that this group is generated by these 6 actions, that means that just having 6 of these things can generate all 4.3 times 10 to the 19th actions of the Rubik's Cube. In other words, from here or from anywhere, I can get to 4.3 times 10 to the 19th different states. Ever since its invention in the 1970s, the Rubik's Cube has not only attracted the general public, and especially puzzle enthusiasts, but also mathematicians who have asked a number of questions about the mathematical properties of the cube. And one of these is, what is a minimal or minimum generating set? It turns out that this is not minimal. This is an example where we don't necessarily want to use a minimal generating set. Turns out that we can generate any of these actions with the other 5. So there is a way to generate a 90-degree twist of the bottom face with these 5 faces. I don't know how to do it offhand, but it does mean that this Rubik's Cube group is generated by F, B, R, L, and U, and that is minimal, though at least to me that's not obvious at all. Even more amazing is what a minimal generating set is, or a minimum generating set. How about pausing this video and think about, and just take a guess as to how big a minimal generating set is. So how many actions do you need to generate all 4.3 times 10 to the 19th? It turns out that you can do it with the action L squared, B, R, D, inverse, L inverse, and U, F, R, U, R inverse, U inverse, F inverse, and that's it. You just need 2 actions to generate all of the states. I think that's incredible. This is the fact that David Singmaster, who adopted this notation in the 1970s and was one of the early mathematical pioneers of this theory, attributes to Richard Feynman's PhD student, David Barnes. Another really interesting question that mathematicians have asked for decades was, given an arbitrary scrambled state of the cube, what is the minimum number of moves that you need to bring it back to the solved state? Even the world's best speed cubers don't come anywhere near this minimum when they solve the cube. And this question was open until 2010, where a group of 4 mathematicians and computer scientists proved that every configuration of the Rubik's Cube is at most 20 moves away from the solved state. Sometimes this is called God's number. So moreover, they actually found configurations that are exactly 20 moves away. And I should emphasize that for a move here, they're not just using this generating set, but they are also using the generating set of that a cuber would use, where you are allowed to do these inverses, and you're also allowed to do 180-degree twists. So though the Rubik's Cube group is generated by these 6 actions, well, actually the first 5, most solution guides will also use this notation, F, B, R, L, U, and D with primes for counterclockwise terms. And also things like F2, B2, R2, L2, U2, and D2 for 180-degree turns. And this is what cubers will typically consider as a move. And using these 18 possible moves, every configuration is at most 20 moves away. And there are configurations that require 20 moves. We can interpret this in a mathematical language using graph theory or network theory by defining the diameter of a graph. So the diameter of a graph is the longest, shortest path between any two nodes. So it's saying how far apart can there be two nodes, or how far apart is the maximum distance between any two nodes. That's the diameter. And this result in 2010 in that language says that the diameter of the Cayley graph of the Rubik's Cube group with the following generating set, so 18 elements, is 20. In 2014, two of these mathematicians, Tom Rokicki and Morley Davidson, with the help of the Ohio Supercomputing Center, solved the Rubik's Cube in the quarter turn metric. So they said that the diameter of the Cayley graph of the Rubik's Cube group, where you only allow quarter turns as a generating set, is 26. In the half-turn metric, there are actually hundreds of millions of nodes that are a maximal distance, which is exactly 20 from the solved state. In this so-called quarter-turn metric, we only know of 3 that are at a maximal distance, in other words, 26 moves away. There might be more, but it's not a state space that we can search pretty easily. It's conjectured that there are approximately 36 nodes at a distance of 25, 150,000 nodes at a distance of 24, and 2.4 times 10 to the 16th nodes at a distance of 23. When we study permutation groups, we will better understand why the quarter turn metric is more natural than the half turn metric mathematically. We can talk about the parity of a permutation being even or odd, which we don't get in the half turn metric. I should say that this was done with the Ohio Supercomputing Center, but the result 4 years earlier about God's number being 20 was also done with massive computational aid. In the remainder of this lecture, I want to show you some other puzzles that involve the theory of groups. Let me start with telling you about a really neat book by Jamie Mulholland, who's a professor at Simon Fraser University in British Columbia, Canada. He has self-published a book called Permutation Puzzles, A Mathematical Perspective, that, as of this recording, is freely available on his website. He goes over a whole bunch of puzzles in there, but there's 2 that he uses especially a lot, and those are the following right here. This first one is called TopSpin, which was developed in 1989. I actually played with this as a kid. I was born in the early 80s, and I remember having one of these and probably forgot about it for probably 25 years until I read this book and saw that picture, and it rang an old bell. The other one is called the Hungarian Rings, or Rubik's Rings. And this is a toy that dates back to the 1800s, but it was popularized after the Rubik's Cube by a Hungarian engineer, and then was, I think, in the 1980s, and then was released by a different company in the United States under the name Rubik's Rings in the late 1990s. And I'm sure there's other versions of this that exist out there. So for the first one, there's this track of 20 beads. They're cylindrical, like coin type things. And you can rotate these in a circular motion, either direction. And you can also, there's this little turntable where if you have 4 beads in here, you can rotate this 180. So swap the order of these 4. And so you scramble this up, and the goal is to try to get it back to the solved state, which is where all the numbers are in order. This one here, it should be self-explanatory. These things are balls, and you can rotate them around either circle. So you scramble it up, and then you try to get it back. There's no numbers in here, only colors. So you can find this book, and And actually a whole bunch of applets that Professor Mulholland has written on his course website. I think if you add the word applet or applets, I think plural, after this, you will get to those. Another great resource is Jap's puzzle page, which you can find here. And I don't know if this video will outlive these websites, but you can use Google, you can use the Wayback Machine if these websites are no longer up. But on this page, there are literally hundreds of puzzles like this, where the author analyzes the mathematical properties of. In some cases, there's applets or there's pictures. There's a whole bunch of Rubik's Cube variations, like 2x2s and 4x4s, and there's like tetrahedral and dodecahedral, all sorts of things. It's really fun to check out both of these websites. But for a moment, let's think about how groups arise. So if you think about the Rubik's Cube, there was a difference between the actions of twisting the cubes, like left, left, top, top, bottom, versus the configurations. But like we saw with the rectangle symmetry group, there is this bijection, this one-to-one correspondence between the actions and the configurations. And for this one, it was natural to label the home state as the unsolved state as the home state. Same thing here. We can talk about actions of this as rotating, etc. And there's some ambiguity as to whether or not you want to consider all 20 rotations of this to be the same state. Are you just looking at in other words, are you considering a state by the cyclic ordering of these, or by which beat is right here? But you can use either convention and you get different groups. But it shouldn't be too hard to think, to look at the analogy between the actions and the configurations of this puzzle and that of the Rubik's Cube, or if you prefer, the two light switch group, or the coin 2 group, or even like the symmetries of the rectangle and the triangle. And the same thing here. This one doesn't have that ambiguity about whether cyclic rotations are the same state. So there's two generators of this. You can rotate. So all configurations are generated by either rotations of this ring or by this ring. Whereas over here, the generating set is either rotate this or twist this 180. Our next puzzle was invented in 2011 by the father-son team of Andrew and Alex Sutherland. Andrew is a professor of mathematics at MIT, and his son Alex, at the time, I think was in his last year of high school. They developed this puzzle, played on an M by N grid, though most of the examples were on a 3x3 grid because it's complicated enough in this setting. And they also wrote an app for iPhone and Android that was on the App Store for a couple of years, though it's no longer there. In this puzzle, a legal move consists of rotating rectangular regions by 180 degrees. For example, if you take this is called the home state or the solved state configuration, and you identify this 2x2 subregion and you rotate everything by 180, you can see what happens over here. These numbers are rotated and they're upside down. Unlike what I did with the rectangle puzzle, the rectangle symmetry group, I will keep these numbers upside down because that's what they did. If you have this 1x3 region and you rotate that 180, then you see that the 3 and the 5 swap places and everything gets rotated as well. There's all sorts of questions you can ask about this, like given a scrambled state, how quickly can you return it to the solved state? Or if you randomly generate a state, a state like this, is it even solvable? And if you generate one, and if not, then what's the probability that a randomly generated grid is solvable? A lot of these questions were explored for general N and M, though the 3x3, again, is the one that was the most common because it's simple yet complicated enough to be a hard game. And this is what they built on their web app. Fast forward a couple years, and Dana Ernst at Northern Arizona University wrote a fantastic book on abstract algebra that uses Cayley graphs. It was also inspired by Nathan Carter's visual group theory, so I encourage you to check it out. It is open source and freely available on his website. I will caution you that he considers multiplication being done from right to left instead of left to right. So just be mindful of that if you are looking at the Cayley graphs. But he started out this textbook with this game, Spinpossible, as an example of groups, like how Nathan Carter in his books began with the Rubik's Cube, and how I started with the symmetries of the rectangle and the triangle. So a couple years later, him and Jeffrey Sly, who's a professor up in New York, wrote a paper on teaching abstract algebra with Spinpossible. And Jeffrey Sly wrote an app. So you can play this on his website. And here's a screenshot of what that app is. Now, they have since called this Spin3x3 instead of Spinpossible for copyright reasons. I don't think they're really worried about getting sued by a professor at MIT and his son. Perhaps they're worried about being sued by a person who owns the Spinpossible website now. If you look at it, it's actually someone who's really into knitting and teaches classes on knitting and spinning. I don't think they're really scared of being sued by him either, but I think just to be safe, they're giving it a different name and they call it Spin3x3. So they have a paper about using this in the classroom, which is worth reading. And then you can check out this in the original book on Dana Ernst's website. In 2024, David Nacin, I don't know if I pronounced that correctly, a math professor in New Jersey, published the group theory puzzle book. Here's the cover and the table of contents, and even though we haven't covered these terms yet, the listeners who are familiar with group theory should recognize a lot of these: cyclic, abelian, dihedral, permutation, quaternion, and cosets. So I encourage you to check this out. Finally, I want to finish with perhaps the most famous mathematical group theory-ish puzzle outside of the Rubik's Cube. That is the so-called Impossible 15 puzzle, which was a craze in the United States in the 1870s and 1880s. Here's a modern version of it, and the idea is that there are 15 blocks on a 4x4 grid with one empty space, so you can slide these blocks around and fill that space. And the original puzzle, two of these numbers were swapped. I forget if it was 1 and 2 or 14 and 15. It doesn't make a difference, but the goal is to return the puzzle to the original state. And this is impossible, and this has been mathematically proven because it has something to do with the parity of the permutation. You can only realize even permutations on this board, and swapping two adjacent blocks is a so-called odd permutations. We'll learn about this in the next section, what permutations are. But an 1879 American Journal of Mathematics paper, like what happened 100 years later in for the Rubik's Cube, this attracted mathematicians right away. So Johnston Story wrote the following: the 15 puzzle for the last few weeks has been prominently before the American public and may safely be said to have engaged the attention of 9 out of 10 persons of both sexes and of all ages and conditions of the community. I find it remarkable that something was that popular that 9 out of 10 people have been engaged with it. I don't think even Wordle was that popular at its height, and this is before the internet. So they actually proved that this puzzle was impossible, which is, but news traveled differently back then than it did now. So the general public still engaged with it for years because there were actually cash prizes for anyone who could solve this impossible puzzle. Similar puzzles to this have popped up since then. One of them is the so-called Panama Canal puzzle of 1915. This was, here's directions from a newspaper, and Same idea. You take out this block and you rearrange things and you try to respell Panama. And this time you can actually do it. And this brings up questions like, is it because it's 6 by 2 and not 4 by 4? Of course, it's easier if the A's are indistinguishable. And in this case, like these two particular A's, it's really hard to tell if they're out of place. You can't swap these two A's. There's versions of these puzzles where some tiles are indistinguishable or not. This is a little bit different than the puzzles that we saw earlier, including the Rubik's Cube and the Spinpossible and the Hungarian Rings and the TopSpin, because you can't always compose actions in these puzzles. There's some times where you get stuck. Like you can't move down this first block here. So this puzzle's algebraic structure is something called a groupoid, which is like a group-like thing. It's got the property, it's got the inverses, it's got the identity. It just doesn't have the closure of the actions. Now, there are group theoretic ways to represent the states and the actions in here. So you can actually realize this as a group action, which is a topic of chapter 5 in this series of lectures. So it's not to say that there aren't groups involved, it's just not as straightforward as every possible action is an element in the group and can be composed. So this picture was taken from Jim Storr's Puzzles homepage. He's a professor of computer science at Brandeis, and he has a couple dozen puzzles like this where he's explored the mathematics of it and the combinatorics. And I encourage you, if you're interested, to take a look at that. And if not, I hope that you will stick around for the next lecture. We'll talk about group presentations, and this is how you can write down a group algebraically to encode a Cayley graph. So stay with us.